All right, one last video with bonding formulas for differentiation. This is now part 3. Part 1, so the idea is we look at these two derivatives. Derivative of x to the fifth is this. Derivative cube root of x is this. What happens when you multiply by a number, add those functions, subtract those functions. Part 2 talked about the product rule, when you multiply them together, quotient rule, when you divide them. And now it's time to combine them in the other way that functions combine, and that is chain rule. Cube root of x to the fifth. And so for chain rule, this is a bit different than the other ones because the functions are not just being multiplied or something. This is chain rule, and you have to be mindful of what these functions mean. We're looking at something like the derivative of f of g of x. So the way I like to think about this is what is going on with this f of g of x. An example I like to give is the following. So suppose we have a hill on the coordinate plane, and that has a slope, that is a rise of 1 mile per, that's a crazy slope. Let's go with a slope of 1,000 feet for every mile it's approached. So our x units are in miles, and our y units are in feet. And obviously, I'm not drawing it to scale, or at least not a square scale. So the slope of that hill is 1,000 feet per mile. Now, I've got a bicyclist, or just a walker, who is walking east at 5 miles per hour. Now, what I want to highlight is that is not the along the hill distance. That is if he has a GPS tracker, and based on a satellite looking down, he is moving eastward at 5 miles per hour. So the question is, how quickly is he moving up? Is the hill pushing him up as he moves to the right? Well, if he's going 5 miles per hour, and the hill goes up by 1,000 feet up. This is miles east. Per mile east, if I'm going to be more specific, we multiply those together. Some units cancel in some meaningful way, and we land with 5,000 feet up per hour. That's how quickly he's moving upward, which makes sense. If he's moving 5 miles an hour in 1 hour, he's going to go 5 miles, and it's going to go up by the corresponding amount. 5 times 1,000 feet is going to go up by 5,000 feet in that 1 hour, but that also scales in general as a per hour situation. So here, our rates are adding. This is one function, this is times another function, except our functions are kind of boring. It is a slope function and it is a speed function. Still, the same principle applies. Because what we're looking at here is the derivative of f of g of x is, for example, it is how quickly is g moving and how quickly is f moving. So it comes down to the rate at which f is moving times the rate at which g is changing. And that by itself, without what's inside the parentheses, makes sense along with what we've been doing here, that rates multiply when they are being compounded. The tricky part is why that should be g of x, but it's really just cutting and pasting the inside there. We want to make sure that we're looking at the speed of f at the appropriate time. Here it's not as much of an issue because it's all constants anyway. But consider the following example that's a bit more complicated. Say I've got a function, now instead of a hill, now my function is y equals x to the fourth. Horizontal motion, now he's going back and forth. And let's say that is, we haven't done trig functions yet. Well, You're going to learn a new thing here. We'll say the horizontal, the left and right, is based on sine of t. Because that will get us the back and forth motion that I'm trying to describe. Well, that means his height at any given time, the height of the walker is sine of t, gives you the horizontal. Then once you have the horizontal, you raise it to the fourth to get the height. So we go from time, and then the blue function gets us our x-coordinate, and then our green function translates that x into a y, and that gets us our y in the end, which is sine of t to the fourth. Raising an x-coordinate to the fourth is going to be how you translate a horizontal into a vertical. So if we wanted how quickly his height is changing at any given time, that would be h prime of t, which, according to our formula from before, that is 4x cubed times how quickly sine is changing. Well, okay, so it's, for the moment, I'll write an x there, because that is the slope of this height. If he is here, it explains how quickly it's going up, which is a local hill. And this will be how quickly this will actually be his speed, his horizontal speed. Horizontal speed. And that, as it turns out, derivative of sine of t is cosine of t, assuming t is in radians. There I'm using a bit of a thing we haven't discussed yet in the elementary functions, but it's another elementary function that we'll want later on. But x is not x. We need to be writing this in terms of t, so we translate it back into the original language of t's. So that's sine of t, x cubed times cosine of t. There we've got our f prime times g prime of t. And that's our g of t. Because f of x is x to the fourth, g of t is sine of t, and our h of t is f of g of t. So here's our f prime is of whatever the input is that input, 4 times that input cubed, and our g prime is, well, what I have up there. So this is how chain rule is going to work. It's a matter of recognizing the functions at play, though, in practice. This is why it is what it is, but often it's the application that gets to students. And so I want to take a look at a few examples of that. So say we have the function, so we're trying to take the derivative of the function square root of x cubed plus x. The key feature here is to recognize what is the last thing that happened. If I were to actually substitute in for x to try to figure out a value for this function, what is the last thing I would do? What is the last action taken? So if we were substituting in for this, if that's our f of x, f of 3 would be this, 3 cubed plus 3 square root. But the way you would do it, or you would cube that, and you would add 3 to it, and then you would then you would add those up, and then the last thing you would do is take the square root. That's what we want to identify here. And so this, you could write this as x cubed plus x, and then I'm going to do this in red to indicate the outermost function. The last thing that happened is the taking to 1/2 power. That's our f. Not this f, but the outer function. That's the outer function. And then the rest can be thought of as an inner function, which itself may be made out of an inner and an outer layer, something like that. That doesn't happen here. And so we're going to peel off that outer layer, that 1/2, and say, well, what would that do as a derivative? It would be 1/2 times whatever's on the inside to the negative 1/2. And then it's a matter of cutting and pasting. X cubed plus x. But then what chain rule dictates is that you multiply that by the derivative of that inside. That's the g prime of that's the g of x on the inside. There's the g of x. There's the g of x. Right. So this is 1/2 x cubed plus x. So the negative 1/2 times. Right now this is just a matter of doing a power rule and a sum rule there. And I do want to highlight the parentheses here. There's a difference between without the parentheses, where it is this mess times 3x squared, and then you add 1 at the end, and this mess times this quantity. Because when you go to simplify it, this is 3x squared plus 1 over 2 square root x cubed plus x. That is as simple as I really would want. So 3x squared plus 1 over 2 times square root of x cubed plus x. And this is one of these functions we do not have any other rules for it. I mean, you could, I guess, try to do the limit of this, as plug in x plus h and all that. You don't want to do that, though. It's a giant mess. It's doable. You multiply by conjugate and all that, but you don't want to do that. That's the beauty of chain rule, that we don't have to. And all these differentiation formulas. Let's take a look at one more example here. Take a look at the derivative. Look at how bad this can get. So the derivative of the square root of x plus, I already talked about sine, so I might as well use it again, sine of x squared. And it's always a matter of looking at, when you're looking at this, when you want to look at the outer of the same inside times the derivative, outer prime times the inner prime, in some sense. So I'm looking at this. What is the last action that happens? It is the square root. That is the thing I want to peel off and handle first. So just like I turned that into a 1/2 power in the last problem, it's the same thing. 1/2 times whatever's inside the square root. So 1/2, and I'll color this in blue. So that'll be x plus sine of x squared. And I really recommend writing it like this, not trying to do too many steps at once. You don't get bonus points for doing it in as few pencil strokes as possible. Let's simplify this a bit. That's 1/2 x plus sine of x squared to the negative 1/2 times big old parentheses. All right, well, that's a product, that's a sum rule, so 1 plus the derivative of sine of x squared. Well, that sounds like that's going to be messy, so I'm just going to put that in as a placeholder for the moment. At this point, we can either work in place, or what I'd like to do, go off to the side, and we'll focus just on this little piece, and then we'll substitute. That way I don't have to constantly be rewriting this part. That seems like wasted effort. You know, there's trying to do too many things at once, and there's being efficient. Right, so now we're trying to do this. Now note, this itself is going to involve a chain rule. Sine is now our outer function, and the x squared is our inner function. So derivative of sine is cosine of whatever's on the inside times the derivative of whatever's on the inside. Well, that's 2x, which we traditionally write out in front. Cosine of x squared. I take that, and I plug it back in for the squiggly underline. And so our end result, this derivative will be 1 over 2 square root x plus sine of x squared. The square root coming out of the negative 1/2 times 1 plus, the quantity, 1 plus 2x cosine of x squared. I can move that up top, I guess. I don't really know why I'm bothering. Just tradition. And that would be our derivative. Yes, it's a mess. Yes, it's layered. Be diligent. Be careful. Don't be a hero. Don't try to do as many steps as you can in one go. It's more efficient to do it right the first time than to try to do lots of steps in your head and end up doing it 3 times until you get it right. All right. Plus, it shows your instructor all the work that you've done. All right. That is the chain rule. There's a few other versions of it. There's one involving Leibniz notation, where dy dt, if you think of that as dy dx times dx dt, this is the slope, and that is the horizontal speed that we were looking at in the beginning of the video. That's another way of looking at it, but this is going to involve a lot of trading one variable for another that typically is not that much faster than doing it with peeling off the layers. And that is the chain rule.